Alright, so once you have OOMMF up and running, you want to run a simulation. And to do that, you're going to need OOMMF code. And the thing about OOMMF is that it has varying types of code based on the version of OOMMF you downloaded. So in the window, in the OOMMF window here, you can actually see this problem ED. If you click on that, that's actually a OOMMF 1.1 problem definition um, window that comes up, and it allows you to describe things like material parameters, simulation details, part geometry, and so on and so forth. What I'm going to do though is rather than using OOMMF 1.1, I'm going to use OOMMF 2.1, which is doing basically the same thing but with code written in kind of like C language. So I have this file called disk here. I'm just going to double click on it. And this is an OOMMF 2.1 code that is just simulating a disk of permalloy, which is a nickel ion alloy. And the code starts off with the setting up the pi and mu naught constants, a random number generator, and it starts off with an image atlas, which describes the range of the disk. So it's a 400 nanometer by 400 nanometer disk, and it's 25 nanometers thick. And I'm using this image disk.bmp, which is going to be a file of a picture of a disk that is basically imported to the software. And view plane meaning XY, meaning I'm looking at the disk in the XY plane. Color map basically means any colors I have in the disk file, the BMP file, I have to describe what the colors mean. Are they magnetic, non-magnetic, semi-magnetic, things like that. So once you have that set up, then you want to go into the multi-atlas. Multi-atlas just kind of puts a global atlas as the atlas being referenced, and you can put multiple atlases under here. So for instance, as I described image atlas of MBuffer here, I can describe a second one and I name it MBuffer2, for instance. And then under global atlas here, I can describe the atlases as both MBuffer and MBuffer2. So OOMMF knows to refer to both of those atlases. And then you're going to create a mesh. So OOMMF works by discretizing the file you give it. So the geometry of the part that you're going to be simulating is discretized. And the thing about it is that it has to be integer multiples of the dimensions. So the cell size which I'm using is 5 nanometers by 5 nanometers by 25 nanometers. Here they all have to be integer multiples of the x, y, and z ranges here. So 5 nanometers of the x, 5 nanometers for y, and 25 nanometers for z. The z direction can also be 5 nanometers, but it will take much longer to run. So I'm using 25 nanometers for the purposes of the simulation to get the simulation to run faster. And again, I'm going to reference the atlas here. So this cell size is determined by the magnetostatic exchange length, which is given by 2 times the exchange stiffness constant divided by the square root of the mu naught, which was defined up here, and the magnetization, the saturation magnetization squared. So it's given by this relationship here. And what you want to just make sure of is that your cell size is smaller than the number that this comes out to be. So I think for the purposes of the numbers I've used here, this expression comes out to be about 5.29 nanometers. So I'm using 5 nanometers as the cell size. If your cell size is larger than your magnetostatic exchange length, which is described by this expression here, you will not be able to get a thorough description of what your system does under certain conditions. So for instance, if your magnetic moments are supposed to curl into a vortex, for instance, you will probably not see that happen. So you just want to make sure that this cell size is small enough to make sure that you're capturing all the details, all the simulation dynamics going on within your simulation. The important thing to note here is that the smaller the cell size is, the longer it takes to run. So it is not uncommon for OOMMF simulations to run from several hours to several days if you're running a large enough atlas. So just keep that in mind. What it tells you is that you have to have a large enough memory while the simulation is running, because it can be quite frustrating to start a simulation, walk away for a few days and come back and see that you ran out of memory and the simulation stopped halfway through. So just make sure you have enough memory. I'm going to be using uniform exchange. So there are different types of exchange that can be used as per the OOMMF documentation on their website. So in this case, I'm just using uniform exchange, and I'm giving the constant A this value here. And then I'm going to move on to anisotropy. So anisotropy just refers to the uneven geometry of my part. So I'm going to be using a thin film here, so I'm going to be neglecting the anisotropy. So I'm going to be using uniaxial anisotropy here, where the K constant in the anisotropy equation is 0, and I'm just using it as a random vector field here. And then the applied field, also known as the Zeeman, can be written in terms of an H range such as this, so what I'm doing here is converting the field values from Tesla to M meter by multiplying M's per meter by multiplying the numbers in this brackets here by this expression 1 over mu 0. So basically I'm just converting 0.15 Tesla to M meters. So everything within this bracket will be multiplied by 1 over mu 0. And for the H range, what it's doing is it's starting at 150 M's per meter, 150 M's per meter in the X and Y axes, and 0 in the Z axis. So it starts from there and it goes to 0, 0, 0, and it takes 5 steps to get there. And then similarly going from 0, 0, 0 to negative 150 amps per meter, and so on. So basically what this is doing is drawing a hysteresis loop, and you'll see that when the simulation runs. And then there's the demagnetization that doesn't take any arguments within its bounds, so you just leave that as is. And then you can move into the solver. So I'm going to be using the spin transfer evolve solver here. There are other solvers that can be used here, but for the purposes of this simulation, I'm going to be using the spin transfer evolve. And basically what the solver entails is it enables the precession of the magnetic moments. It's using the Landau-Lifshitz gamma value as 2.21 e to the 5. The alpha value, so this is the dampening factor in the Landau-Lifshitz-Gilbert equation. This equation, this factor is pretty important when you're running your simulations. You have to make sure it is small enough that you're able to capture the simulation dynamics. So I would say for most purposes you probably want to start with somewhere around 0.05 to see if your simulation progresses as you expect it to. Experimentally, I believe it's been determined to be somewhere between 0.1 and 0.01. So you just have to go through trial and error of whatever value works for you. The lower the value, though, the longer the simulation takes to run, so keep that in mind. And then these are just other parameters that come with this particular solver, and you can change those numbers to whatever you want. So the time driver, which is just the time aspect of the simulation, basically just using a base name disk. The vector field output is binary 4. You can change that to text as well, so that you can take the output files that OOMMF generates and get them in a text file that you can use to plot in other plotting software. The evolver, which is the SpinX for evolve that I'm using here, I'm describing what my stopping condition is for each stage of the simulation. So for instance, the stages that are going to be run are going to be 20 of them here for 5 steps for each of these Zeeman ranges here. When the torque is less than 0.001, that's going to be the stopping criteria for that stage. And the saturation magnetization is described by an atlas scalar field, where I'm describing the atlas, the default value, and then the regions of the image file that I gave it. So non-magnetic means there is no saturation magnetization. The universe, which is just the rest of the image, is also zero magnetization. And then the magnetic portion has this value for the saturation magnetization, which is a literature value that you can see is often used in literature. And then I'm starting off with a initial magnetization of 000. You can change your initial magnetization to, let's say, the starting point of this Zeeman range here. That works as well. But you can change it to whatever you want. Actually, let's do that. And then the rest of the code here is just simply describing what I want OOMMF to output. So destination MMGraph and destination MMDisp. So MMGraph is going to graph the hysteresis loop that I'm going to draw, and MMDisp is just going to be the vector display showing the magnetic moments during the simulation. And this part of the code here specify how often to update MMGraph and MMDisp. So it's basically just saying by the time driver magnetization vector updated every 1 second, and the time driver magnetization for my display is these two guys here. So my graph and my display. So my graph here is scheduled for 1 to be updated once, and then my display is scheduled to be updated once with a step of 1. So updated every stage, and then the step once every second.